Thank you.
Okay, our next short talk is by Tahina from Microsoft Research.
Thank you. With my colleagues Jonathan Protsenko and Nick Swamy from Microsoft Research Redmond, and Antoine Dunia and Cédric Fournet from Microsoft Research Cambridge, and former interns of ours, Haubin, Nadim, and Tej. We have been working on Everparse, which is a verifying compiler that takes data format descriptions as input for binary packet formats, for instance, and automatically generates verified efficient parsers and serializers. Everparse is part of Project Everest, which our goal is to implement and verify the implementation of TLS 1.3 and also previous versions, for which we would like to prove some security properties as well, confidentiality, integrity. So our implementation is mid-TLS, and it relies on Evercrypt, which is a verified implementation of cryptographic algorithms and cryptographic primitives, for which we also prove some side channel resistance. And Everparse, which allows us to develop verified and implement verified parsers and serializers for the TLS handshake message format, for handshake packets. And for all of those, of course, we also prove memory safety and functional correctness, of course. And so, Everparse, how does it work? So, you write your data format description, such as the one that you can find in the TLS standard. So, it's basically a data type description with dependencies on sizes, on enum values, and so on. And from there, we automatically generate a format specification in F star along with verified implementations, low-level implementations in the low star subset of F star, which we then extract to high-performance C code. Our low-level implementation, yes. We generate the format specifications of parsers and serializers, for which we prove that the serializer is correct with respect to the parser, so functional correctness, and also some security properties, such as the fact that any high-level data has a unique binary representation, so that you can avoid the bugs that have happened in the past for a blockchain. The fact that you could say, yes, I sent you 2 Bitcoin, and here is the hash that should tell you yes, but in fact you actually sent me only 1 Bitcoin, but because the transaction for 1 Bitcoin has 2 possible representations, and one of which shares the same hash as the transaction that that you claim to have sent me 2 Bitcoin, then this was actually an attack that is suspected to have led to some large-scale theft in 2014. So this is a kind of security property that we automatically prove when generating the specification and the implementation of our code, of your parsers. And our verified low-level implementations are zero copy, in the sense that when you want to check that some bytes are valid with respect to your data format, you don't necessarily need to construct the high-level value. And that's what we call validators, and from there we manage to be more than 10 times, for instance for Bitcoin, more than 10 times as fast as the Bitcoin Core usual implementation. And so we have been applying Everparse for TLS, Bitcoin certificates, and also Quick and other also internal usages within Microsoft. Open source, you can get it on GitHub. Right, thank you. That we generate C code. I'm not sure from the latest of what I read from Narcissus whether they are generating more than just a camel code. But generating C code that is efficient in terms of, at least for parsing, that one, we generate validators that do not build the high-level value, and then we also generate accessors that assume that the validator has been run and has replied that yes, your data is correct, in such a way that those accessors can directly read from the input, your input bytes without any copies. And this, I am not aware that Narcissus does anything like that, and I don't think so from what I read last time. So one thing. And the other thing is that the dependencies are, all dependencies are pure, and so it's easier for the user to express the specifications because we don't need anything like, at least for TLS, quick or anything, stateful specifications.
Also the kind of grammars that they look at are different.
Voilà.
Here you want to have this injective encodings.
Also, yes.
While they look at encodings that are potentially non-deterministic. And for crypto, that's very bad.
Thank you, Tahina, for... Yes, you.
Sorry. It's all good. So I'm curious to hear a little bit about the TLS, not the Bitcoin thing. So, like,
yes.
I'm thinking as for TLS, you have, say, X509, but certain keys have their own templates that they come with. Like, how do you deal with templates at runtime or you don't?
Alors, this I think Antoine will be able to answer more, but he's not here. I'm more on the parser side than the actual TLS implementation. You can read the, yes, you can read the Unix security to the 19 paper for your question. And
Tahina, I can
yes.
respond if you want. We delegate X509 parsing to an external library.
Okay.
For two reasons. One, we want to scope our verification, and second, in the real world, no one wants a new X509 parsing library. They want to integrate it with whatever the system one is on Windows or on Linux, so we don't have a lot of traction when we library. They're just like, give us entry points and we'll put it out in the system. It would be nice to do X509. Yes.
That's the last question.
So I was wondering about, like, in TRS style standards, you often have fields that contain random data, right? So I was wondering how you deal with that.
Alors, the semantic whatever semantic validation is deferred to the code. That is what we support for validation are dependencies with respect to enum values and sizes.
But I mean, is property saying that there's a unique representation?
Yes.
But if your serialization has to generate random data.
No,
or you do the random data before.
Yes, the random data is done before. Sorry. Yes.